All right, hello and welcome. In this video, we're going to look at this RLC circuit. It is a series parallel combination circuit, and they've given us a frequency of 25 kilohertz. And so we know we can use that to find our XL value and our XC value and use that to determine our total current and all of our power values. And so we're going to start with total current. Our total current says that we need Ohm's law, right? We need current is equal to our voltage divided by our resistance. In this case, it's going to be our total, right? Our net reactance and our linear resistance, and we're going to call that our impedance, right? ZT. But our voltage source stays the same. That's 16 volts there, and so we'll plug that in once we figure out our ZT. That's going to be our first step. ZT is equal to, and that requires the knowledge of our total RT squared, and we will add that to our X total squared. Right, so now we need to figure out what those two are. We need to find RT so that we can plug it in here. We know we got two resistors here, and so we'll have to figure out their relationship to each other. We also know that X total is equal to our XL minus our XC. We don't have either of those XL or XC, so we need XL and we need XC. Right, but before we can do XL and XC, we actually need to solve for our total capacitor and inductor values. And so we need to find LT and CT. Right, so we're going to start with those two first, as well as our total resistance, and then we can plug in as we go and solve for our total reactance. And that's going to get us the ability to plug into our Ohm's law over here. All right, so let's start with that. So we know that our resistor comes in here, that we're only going to focus on resistance right now. So we're going to ignore the fact that this inductor's here, that these branches parallel out here, and they come through, and they come back down and go through this capacitive load until they come back all together at this final node here, and it goes straight through the next resistor. It has no choice but to go through R2. Right, so that means that R1 and R2 in terms of linear resistance are going to be in series with each other. Right, so we'll say R1 plus R2. And we know that that's 120 plus 100, and that's going to give us a 220 ohm. Oops. 220 ohm. All right, so know what our RT, that's going to be the first thing we plug into our total reactance equation, but we also need to find our LT, and we're going to do the same thing. We're going to ignore our resistors and capacitors and just deal with our inductors. And when we do that, we see that we have no choice but to go through L3, hit a parallel branch where L2 and L3 are in parallel with each other, and then that branch comes into this central node here, which puts them together again, right? So it's just RL, L1 and L2 in parallel with the series of L3. Nothing else matters in the circuit. It loops back around into a series and gets us back to the end here without any other branching. And so that's how we're going to write that. So let's do that here. We'll say that we have L3 in series with, we'll open parenthesis for this parallel node here, and say that that is L1 in parallel with L2. And we can solve that out and get our LT out of that, and then we can use that in our XL equation. So let's do that. We'll take it step by step here. We'll say that we have a millihenries for each, and we know that when we put two of the same inductors or resistors in parallel with each other, we end up basically taking that value and dividing it by 2 when they are the same. And so we can say that we have 1 millihenry. So that's all in millihenries. We double check that also, but we have 1 millihenry. We can divide that by 2, and that's going to be the parallel of L1 and L2. And then we can add that to the 1 millihenry of L3. And so we expect the combination of those 3 inductors to be 1.5 millihenries. Right? So let's do the same thing for our CT here. We can solve for that and say that our CT does something similar, but it skips through the inductors. We go through the inductors and end up at this node branch here. This node branch is like the plus thing in the middle, right? So we know that whatever's before that node, because they're shared right there, it's going to be in series. Right? So the inductors right here in parallel with each other are in series with the capacitors that are next. Right? And so just don't get fooled by that node. Again, we're only focused on the capacitors, so we're going to go up to this node where they start to split and see that our capacitors go up and down at the same time there. So those two are in parallel. And afterwards, they combine back together. So they're only in parallel with each other. There's no other capacitors in the circuit before we return to ground. And so we're going to combine those in parallel with each other. Remember, capacitors in parallel are kind of backwards from everything else. Right? We'll say that we have C1 in parallel with C2. And we know with capacitors, we're just going to add those together. Right? So parallel capacitance add together. Series capacitors are the tricky part, right? They go into that 1 over 1 over equation. So we're going to say that we have nanofarads. We got some weird numbers here, so we're just going to type them in as we see them. 10 times 10 to the nano, which is -9. And then we will add that to our other capacitor there, which is really small. It's that 0.001 times 10 to the -6 for that micro. Okay, so now we have a number to the -8. We'll move that over to the -9, get it at a nanofarad value. So we'll say that we have, move it back one, we'll have a 1, 1, and that's at -9 there, so we'll put a nano, and that's in farads still. Okay, so now we know our inductor and our capacitor value in terms of their total and our resistors in terms of their total. So now we just need to plug it in. We need to plug in what we know XL and XC equal. So let's write those ones out. We know XC is equal to 1 over 2 pi, our frequency, times our capacitance total. And we know that our XL equation is equal to almost the same thing, but minus that 1 over section. So that's just going to be 2 pi, our frequency value, multiplied by our LT. So we'll plug in for both of those and we'll solve out. Let's start with our LT there. We'll say that we have 2 pi, that's a rotation around that circle. So 2 pi multiplied by our frequency, that's the speed around that circle. We know that's 25,000, right? That was given at the top beginning. And then we'll multiply by the inductor that we got. That's 1.5 millihenries. Watch out for your millihenries here, because we're going to move that out, but we can just multiply by, we'll open a parenthesis here and we'll say 1.5 times 10 to the -3. Right, just make sure you account for it. You can also put it as 0.0015, and that would work as well. All right, so that is our XL value. It's 236. Right, and that's in ohms now, right? We moved it out of the henries that we had it in and moved it into ohms. So next we can do the same thing with our XC. We'll convert that over. We'll say that we have 1 over. Watch out for your capacitors. Your XC is going to have that 1 over, and when you do total series and parallel capacitors, they're a little bit different, right? So just remember, capacitors are just a little bit different each time. We'll put 2 pi on bottom, multiply that by our frequency. That's the same as the last one, 25,000. And then we will multiply that by our little capacitor value we have here. That's 11 nanofarads, so times 10 to the -9. We'll close that off. And that is our capacitor value in terms of ohms, right? So 579 ohms, and that is our capacitive reactance, right? Capacitive reactance, inductive reactance was our inductor value, and that's XL and XC. Now we can plug into our total net reactance, right? We know that that's this X total value, and we can do that because we have XL and XC now, so we can just subtract those two and get a value for that out. We'll set that out here and solve for that. We'll say that we have XL minus XC, so 579 will be the second number we write. It's going to be negative, right? The capacitor is going to win. 236 minus 579. Right? 236 minus 579 gives us negative 343 ohms. Right? This negative is just telling us that capacitors ended up bigger than the inductors. The reaction from our capacitors ended up larger than the reaction from our inductors. Okay, so just don't get fooled by that one. Keep that negative in for that rectangular transformation for the theta value, right? Okay, so we're going to keep going. We can plug into our Z value now. We know that ZT at the top here, and that's going to be this RT squared plus Z total squared. We'll send that in there. We'll say that we have the square root of RT squared. That's 220. We did that first. And we'll add that to our X total. In this case, we can put a parenthesis here and add in the negative if we want to, but it's going to square it, right? So negative times a negative makes it positive. So we can actually leave that off if we don't want to add that in and know that that's going to be taken care of there. Okay, so now we know our Z total is equal to 407. That's a 0.4, so we can round that. We can just leave that off there. That's our 3 digits, and that's in ohms. Okay, so that got us to our Z. That's not what we want, right? We wanted that ZT value so that we can get the total current out of it. Right? They didn't ask us necessarily for polar form, so we don't really have to go after our phase angle if we don't want to, but that would be that tangent equation. And you can solve for that also and get your current out for that as well. So our voltage source is 16. volts, and we'll divide that by our Z total that we just found. That's 407 at an unknown angle value. We're going to leave that off because they didn't give us an angle for our voltage either. And we'll say that we have, send that out, and we'll say 16. That's 16 divided by 407. So we've got a current of 39.3. So 39.3, and that's in milliamps. Right? That's the total current for this circuit. But we need to know the true power, the reactive power, and the active power. And so that's going to be different values for each. So let's start with our true power. Our true power involves our true resistance, right? And so that's going to be any linear resistance. That's our R, right? So this is going to be our original power equations. True power is equal to the current in the circuit, IT, multiplied IT squared, multiplied by the resistor RT. Right? And that's going to be anything that is linear in the circuit will be multiplied out like that. Okay, so let's do that. We can solve for that here. We know what our current is. It's the last number we had. And so we can say that our answer squared multiplied by our resistor total, which is 220. So the power in our resistors should be, we'll move that over 340. And that's in milliwatts. Right? 340 milliwatts. That's just in those two resistors. So that's our true power. After that, we have our R value here. We can solve for that using our X total, right? Because that's going to be the reactive power. And so that's going to associate with only the X total value there. And so when we plug this in, we'll do the same equation. We'll say that we have this reactive power is equal to our total current, IT squared, multiplied by the reactive total, and that's X total, right? Our net reactance. So when we solve that out, we can say the same thing here, but this time we'll put the 220 in as our net reactance. We know that that was solved up here as 343. We'll leave it just positive like that because our resistance can't be negative. It just identifies that it's a capacitor instead of an inductor. We'll multiply that by 343, and we get a new wattage value for that. We said that our reactive wattage is actually 530 milliwatts. And then our PA, right, our active power. That one's a little bit different. We have to take the two that we just found and plug it into our square root equation to get the active power, to kind of combine those together into a final total for us. And so we'll say that the active power is equal to the square root of our true power squared plus our reactive power squared. We know both of those, right? We just found both of those. So we can plug those in and solve for this one out. We'll send that out here, and we'll say that we have the square root of, both of these are in milliwatts, and so if we leave them in milliwatts, we'll end up in milliwatts, and that's fine. So we'll say that we have a reactive, or a true power of 430, or 340 squared, and we'll add that to our reactive power of 530 squared. Those are in milliwatts again, so we can leave them both in there, and we'll get an answer in milliwatts. We see that there. So our power here, this is a little long. I'll square root that. Our power active is 600, and we'll round that up to 30. And that's in milliwatts. All right, let us know if you guys have any other questions.